Hello, this is our lecture on cross products, lines, and planes. And then I hope we can reach cylinders and spheres within maybe 1 hour. We will situate lines and planes, cylinders and spheres. These are graphs in R3. So recall that, okay, I'm recording now. Recall that, let me check if I'm recording. Recall that we have ended with cross product and its geometric interpretation. Let me recall that here. So suppose we have vectors A and B. So we have A1, A2, A3, B1, B2, and B3. And then we take the cross product of these two vectors. Here is our pseudo determinant formula. And then B1, B2, and B3. Then you get something like I here. Then determinant of the matrix when we cross this one out. Then we cross this one out for J. And then we cross this one out for K. So for I, we get A2, A3, B2, B3. Then minus J, we get A1, A3, B1, B3. And plus K, here we sometimes I have hat, but of course. And then A1, A2, B1, B2. And then you just do this one is plus and then minus the same here. And then the same here. Then here. And then geometrically, if we have vectors, say this is our vector A and this is our vector B. Your vector A and this is your vector B. They are contained in a plane. So let me draw the plane here that contains both vectors A and B. Of course, let's color this. And then our cross product will be this vector, which is A cross B. And then we follow the right-hand rule for the direction of our A cross. So here, if this is going this way, and from A to B, then our I can draw the hand here. So maybe I recall what we have last time. Let's look at how to compute this in numbers. So let me have this remark that if you take the magnitude of our cross product of A and B, this will give you the area of our parallelogram as shown below. Suppose this is your A, this is your B. Of course, you have to project it here and here. And then this is your parallelogram. And then this is your A cross B. Then this parallelogram has this area equal to this. If this is your A and this is your B. Note that we have put here magnitude, so this is just positive real number. Okay, let us consider computing an example of how we do it. So suppose we get two vectors, 2, -1, and 2, and vector B given by 3, -3, and 0, and then we take the cross product of A and B, let's put it in the determinant form here, and then put the first vector in the second vector. And then here we will have, if we will cross this one, we get I, and then this is this arrow. This is this minus this. Let me, this minus this, and then this is 0 minus negative 3 times 2. Then for minus j, we get cross this out, and then 0. This is 2 times 0. Okay, let me write 2 times 0, and then minus 3 times 2. And then plus k, we have 2 times 3. And then minus 3 times negative 1. Okay, pause this a little bit and then compute. It will give you this one is positive 6, and then this one is another positive 6. And then the other one is 6 minus 3. So minus 3. Okay, so in other notation, this is 6, 6, negative 3. So in geometric interpretation, this is a normal to both A and B. Of course, you can verify that if you check this one. Let me shift to black. So 2, negative 1, and 2. If you take the product with 6, 6 and negative 3, you get 0. So verify this. And then of course this is just this. Wait. This is just equal to 2 times 6 minus 6 times 1, or minus 1 times 6. Let me emphasize that. Plus negative 1 times 6 plus 2 times negative 3. Of course, isn't this will be gone, and then this will cancel with the other one, and then you get 0. So here, these are A and A cross B are perpendicular. Or orthogonal. I will not distinguish between the two in my class, but sometimes there are some subtle differences between perpendicular and orthogonal. Depends on the definitions that are used. Anyway, so here we will present quickly some properties of cross product. So the first property is these are not commutative. So if you reverse the ordering, you get negative of the other one. And then the other is A cross B plus C. This is just, you can distribute A cross B plus A cross C. The third is the following. If you have a scalar and then multiply it with the cross product, you can just put the scalar out and then pair it with A, or you just can pair it with B. C is a real number. And then if you have the 0 vector, then we cross it with A, or the 0 cross with A. And then this is just, here we have 0 vector. And number 5, 0 vector, here we have the 0, 0, 0. And then if we cross A with itself, okay, you get 0. Let me put here A, B, and C are vectors in R3. Then, and then a special case for this is an IJK. But before that, let me have the following: A cross B. If you take that product with C, you can just put the B cross C and then that product with A. And then for the special case, if we have I cross J, you get K. J cross K, you get I. And then you have K cross I, you get J. Of course, if you reverse the direction, you get uh, negative K is just J cross I. And also here, K cross J is negative I, and then I cross K is negative J. I think you can fill in the gaps here if you want. So the fact, the important fact here is this non-commutativity of cross product, and then maybe this one. But the rest, if you can't memorize, you can verify by direct computation. And of course, all of them can be verified by direct computation. So let us consider some analog, similar relationship between the angle between of the angle between two angles and then cross product. We will situate this in nice setting. We don't allow the zero vector. So that we have non-zero vectors, and then our C is scalar. Wait, I'm using letter C. This is the big C, this is the small c. This small c, meaning C is a real number. And then the first property is the following: A cross B. The magnitude is just equal to the product of the magnitude of A, magnitude of B, times the sine of the angle between A and B. And the second property is the following: your A cross B dot C. If you take the absolute value, it will give you the volume of parallelepiped. As shown here, if you have here A, B, and then C, then you have an associated parallelepiped here is 3D object. Okay. Now let us consider this example. Okay, I'm doing blue. So find the volume of your parallelepiped. I'm abbreviating because it's hard for me to spell that out, the long word. Determined by the following points. Let us have the point is P, R, and Q. The P here is 3, negative 1, 2. R is negative 1, 1, 2. And Q is 1, 2, negative 4. So here we have some 3 points. And then we will consider no, not a parallelepiped, a parallelogram first. we will consider vectors. So the important is one start point. So say we will start at of course Q, but you can start with B or whatever arbitrary choice. So say start with Q and then form the vectors A and B and B I mean, and then this is just the vector from P to Q, then vector from Q to P and then Q to R. So if you do that, so 3 minus 1, you get 2, and then -1 minus 2, you get -3 and 6. And then the following, I have -1 minus 1, we get -2, and then following the same argument, you get 6. So this is A here is 3 minus 1, you get 2, and then -1 minus 2, you get -3. 2 minus -4, you get +6, and the same here. Okay, let's continue. So here we have two vectors, and then we know that the area is just equal to the magnitude of this. So we want to compute first for the cross product of these vectors, 2, -3, 6, -2, -1, and 6. So first we get for I component, we get -18, and then plus 6 kasi -6 minus -6, and then for the J component we get 12 plus 12 is 24, so just put 24, and then for the K component we get -2 minus +6, so we get what? -2 minus 6 is -8, so this is just -12, -24, and -8. So if you take the magnitude, it's just the square root of -12. Oh wait, -12 squared plus -24 squared plus -8 squared. And okay, compute this very big number. And then, of course, I remind to you that if you are finding it hard to compute, then you can stay as ganito. This is 28, so square units. Sometimes I'm not so very strict regarding square units. Our unitless, so square of some units. All right, now we also compute our volume of our parallelepiped given by associated to vectors A, -3, 5, and -2. Our B is 4, 3, 0, and our C is 5, 2, -3. So the volume is just equal to the cross product of A and B dot C, and then take the magnitude. So how do you compute that? So A cross B first. I, J, K, and then -3, 5, -2, 4, 3, 0. You get, okay, for the first component, you have 0 minus 6. So 6, and then you get -8 and 11. So verify this. course. So first component, you get cross this out. This is 0 minus 6, positive 6. Here, cross this out, 0 minus 4, so positive 8, but negative yung j, so you get negative 8, and then cross this out, you get negative 9, and then what is that? You get positive 9. Okay, that's supposed to be positive here. 9. Let me check. I think I don't have this. Okay. Nine minus minus 20. It's 9 minus 20 is negative 11. Wait, I used eraser. And then you have to dot it with C. You get 6, negative 8, negative 11. Take that product with C. What's C? C is 5, 2, negative 3. This is 30 minus 16. And then what's this? Plus 33. Okay. You just fill it this out. And then the remark is because I get lost in the computation, you can verify this computation here. This is our thing. But essentially, everything is doing. We just fill in the. Okay, I want to harmonize this. My notes are have typo errors, so just correct the notes that I gave. Now we go to, you can pause this and take a break, and then we go to the next topic as we do in class. So we go to lines and planes. So we define M is nana 0, and this is vector in R3, and your point is say x0, y0, z0 is a point in R3. Then the equation of the line is given by the set of points for which your P0 to P is parallel to M is the line through our point E0 in the direction of our M. And then if M is given by A, B, C, then using parameter T in R, the equation of the line is equations given by the parametric equation here. So we get 3 x component, y component, z component. You have the initial part. You get A, B, and C, and then T, T, T here will elemental part. This is called the parametric equation of line, say L. So here, T is our parameter. And then we have the symmetric equation. If none of A, B, C are 0, we have the symmetric equation. Fall down. The symmetric equations, okay, of L is just your x minus x0 equal to y minus y0 equal to z minus z0, but you just have to divide these components by A, B, and C. If one is 0, say A equal to 0, you just have x minus x is equal to x0, and then put the other one, y minus y0 over b, and then z minus z0 over c. So this is just separate this one. Okay. So that's the equation of the line in R3, either the parametric or the symmetric equation of the line. Notice that this is just all of them. This is equal to T. So I will erase. How do you get this one? Just create T is just y minus y0 over B. So all of them is just T. So let's look at some examples. But before the example, let us recall that in geometry, a line is determined by 2 points. Okay, so this is the example. Find the equation of line L passing through point P given by 250 and Q given by 6, 3, -1. So the solution, you get, you can take a vector. Here we can choose M from P to Q or Q to P. But you can choose any. So suppose we will choose P to Q. So M here is just given by the vector 6 minus 2 is 4. And then 3 minus 5 is -2. And lastly, -1. So, okay, then this is arbitrary. You can choose any of them. You can choose this or choose this. Suppose we chose this. And then we can also use our arbitrary choice for P0. Then can use P0 equal to say P, or can use Q. But convention, I will set a convention here. Use P0 the right term is set. Set P0 be the first mentioned point, and then start with first mentioned point for PQ. Example, PQ. Start with P and with Q because P is mentioned first. Okay. So the equation of line L is now given by X, Y, Z. You just put the X0 as 4, -2, -1, and then plus. What's our vector M? All right, wrong. The point is use P0 equal to P. So here we have A is 4, is -2, and then -1. Just put T here, and then T is on R, and then the point is 2, 5, 0. So this is your parametric equation of, our line M. And then for the symmetric, you get X minus 2 over 4 is equal to Y minus 5 over -2 is equal to Z minus 0 over -1. This is your symmetric equation. Okay, that's it. So now we go to plane in space, and then later on we will mix them together. I will use new board. So plane in R3. So I will just draw this. Suppose this is your coordinate axis, X, your Y, and your Z. Oh, wait, Z should be here. And then you have a plane. This is your plane. And then you have a point. Let me highlight this plane. You have a point here given by P0. And then you have a normal vector in P0 that is considered as A, B, C. This is our normal vector at P0. And then, of course, this one has coordinates X0, Y0, Z0. Then the plane has equation. This plane has equation. This plane omega has equation given by number 1, the standard equation. You have A, X minus X0 plus B, Y minus Y0 plus C, Z minus Z0 equal to 0. Then the general equation is just expand this out. You get AX plus BY plus CZ and then plus D equal to 0. Here, D is all these constants. AX0 and then minus by0 minus cz0, because all of these are numbers. So we can combine them all. So remark, if A, B, and C are not all 0, AX plus BY plus CZ equals um, plus D equal to 0 is a plane with normal vector A, B, and C. Where is that? This A, B, and C here. So if you have the general equation of the plane, then you can predict the normal vector. And then I will also add some remarks from geometry. So two planes are parallel if and only if normal vectors are parallel. Their normal vectors are parallel. And also, if you replace this with perpendicular, then you can replace this parallel with perpendicular to the same. Okay. How do you sketch vector of a plane? So sketch. Suppose we have the plane omega given by they're containing P0 given by 4, -2, and -3 with normal vector n equal to 2, -1, 2. Then the standard equation is just 4x minus 2. Okay, no. Your A is this is B, this is C, so 2, and then x minus 4, then minus 1, y minus 2, so plus 2, and then plus 2, z minus is plus 3 equal to 0. If you simplify, get 2x minus y plus 2z. Okay, so minus 8 minus 2 plus 6. So you have 2x minus y plus 2z minus 4 equal to 0. So how do you sketch? So sketch find the intercepts, axis intercepts. So for the x-intercepts, set your y and z equal to 0. You have 2x minus 4 equal to 0. So x here is just 4 over 2. So this is 2. For y-intercept, you have to set x and z to 0. So negative y minus 4 is equal to 0. So here, y is minus 4. And for the z-intercept, so x equal to y equal to 0. And then here we get, what's our equation? 2z minus 4 equal to 0. So z is 4 over 2, which is again 2. And now we can draw this. It's your x, your y, and this is your z. So the z-intercept is positive 2. So 1, 2. The y-intercept, so here is our y. Maybe it's here, negative 4. And then this is not drawn to scale. And then the second one is 2. And then to draw a plane, just connect them. And then maybe put some triangle. Not triangle, but this one. Some sort of parallelogram to have like the illusion of being 3D. So this is the rough sketch of our plane. Okay, so we're done with sketching planes. You can take a pause here, and then we will go to cylinders and spheres in a while. I think before going to cylinders and spheres, I will consider an example that is given in your book. If you have pause, you can continue, and then we will begin with this example. Your plane lambda has points P, Q, and R with coordinates 2, 3, 0, 0, 5, negative 1, and 1, 0, 3. So here we will determine the equation of our plane lambda. So solution, we can take vectors, say A and B. So A from P to Q and B from P to R. So this P to Q is 0 here. So here we get negative 2, 2, 1, and then negative 1, negative 3, and 3. Where do we get this? So B is P to R, so 1 minus 2, negative 1. 0 minus 3, you have negative 3. And then 3 minus 0, you have 3. It's the same way here. And then we have two vectors now. So the idea here is we have A, you have, this is our A, this is our vector B, this is our point P, this is Q, this is R. This is not drawn precisely. And then we take this is the vector, there is a plane that contains both of them. And then we want a normal vector here, which is just A cross B. And then the equation of the plane is we have a point. We can take point P as our point P0 and N as our normal vector. And then voila, we get the equation of the plane. Now our task is to find the normal vector. So N is just your cross product of A and B. So I, J, K. So you just put the components, negative 2, 2, 1, negative 1, negative 3, and 3. So this will be 6. For the first component, we get this is also -1. For the first component, we have 3i. Why 3i? Because 6 minus 6 minus 3. So 6 minus 3 is this is -3 times -1 is 3. So 6 minus 3. And then plus 7j plus 8k. And then this is, I will leave this to you for computation. And now transform this to this form presentation. And then the equation of lambda is given by what's take our first point P be our point P. So this is given by what's point P 230. Actually, you can choose any other point. And we have 3x minus 2 plus 7y minus 3 plus 8z equal to 0. So 8x, oh no, 3 times x is 3x plus 7y plus 8z. And then minus 6 minus 21 equal to 0. So you have 3x plus 7y plus 8z minus 27 equal to 0. This is the standard equation. And this is the general equation of our plane lambda. Okay. So I think you get the idea. And then I have provided similar argument like using cross product to get the equation of the plane, equation of the line. They are running through the same argument. And if you have difficulty understanding them, you can send me a DM. All right. Let's go to the last for today. This is cylinders and spheres. I will go with spheres first. The equation of the sphere with radius greater than 0, radius r greater than 0, and center h, k, l. This is an R3 point is x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. So this is the equation of the sphere, but for equation of form x squared plus y squared plus z squared plus ax plus by plus cz plus d equal to 0. A, B, C, D are real numbers. This may be a sphere, a point, or an empty set. As I will show here. For example, determine the graph of x squared plus y squared plus z squared minus 2x minus 2y minus 4z minus 3 equal to 0. So the solution is you just group them, x squared minus 2x, and then plus y squared minus 2y plus z squared minus 4z. And then you do complete the square. So this is just put the 3 here. So to complete the square, you just add something that will make this component square, square, and square. So what do we add? X squared minus 2x. You complete the square as in Math 27. So we have negative 2 over b over 2a. 2 times 1 is 1. So 1 squared. This is also plus 1. So this is 4. So 4 over 2 squared. So complete the square. So we have ax plus b blank is equal to ax plus something k squared. So we get here, we put negative b over 2a, b over 2a squared. In this case, your b is negative 2, and then 2 times 1. So we get 1. 1 squared is just 1. Here, 1, 2, 1 here. So what we did here, we have negative 3. We add 4. We add 1, and then we add 1. Okay? We get x minus 1 squared plus y minus 1 squared plus z minus 2 squared is equal to negative 3. This is 4, 5, 6 minus 3. It's just 3. Okay. So, since we add something here, okay, I made a mistake. Since we add something at the right-hand side, you have to subtract it on the other side so that it will negate the effect. So we get negative. Wait, I'm getting, let me correct myself. Okay. I made a mistake. So when I transport, I transferred negative 3 to right side, it will become 3. And then what I add at the other side, I will add also at the other side. So we have 3 here. Then I added 4, and then add 1, and add 1. So everything here will be 6 plus 3, 9. So this is 9. So this is your r squared. So this is just equal to 3 squared. So this is a sphere. Wait, I'm wrong. So this graph, a sphere with radius 3 centered at what? This is 1, this is 1, this is 2. So you can draw the sphere. So the sphere is just, here is our origin, and then 1, and then 1, and then 2. Something like here. This is your sphere with radius 3. Yung center 1, 1. Of course, we can do a version of that in which it will just be a single point. So here we get a single point, x squared plus y squared plus z squared minus 2x minus 4z plus 5 equal to 0. So with the same argument, we get x squared minus 2x. Then to complete the pair, we just add 1. And then plus y squared. What's the partner of y? Voila. Plus z squared minus 4z plus 4. And then we get negative 5 plus 4 plus 1. So we just have 0. So this is just a point. So if we simplify this, and then z minus 2 squared, and then x minus 1 squared. Point is given by 1, 0, and then 2. This 1, 0, 2 is the following. This is this one. This is y minus 0 squared. This is just equal to y minus 0 squared. Yeah, 0 for that one. It's a point in R3. And the last example, if we have x squared plus y squared plus z squared, I'll make it easy. Plus 7 equal to 0. So we get x squared plus x squared plus y squared plus z squared is equal to negative 7. So this is always positive. And this is negative. So something positive cannot be equal to something negative. So here the graph is an empty set. So this is like a symbol for empty set. All right. Finally, we will go to a cylinder in R3. So here, a cylinder is just a surface generated by a line. So we call that generator moving along a curve. A given curve such that it is always parallel to a fixed directrix, not lying in the plane of the given curve. So suppose we have this is our directrix, and we have a curve here, and then we want to illustrate this one, and this one will extend to both direction. Then of course we can get something like a surface. So here we have something like a metal sheet, and then of course we cut some portion so that it will be better for our eyes to see. This is your generators. This is moving along this. Let me increase the size. This is your is your given curve, and then this directrix in pink is uh, our generators moving along the given curve, and then the surface generated is our cylinder. Example, if we have x squared, okay, let me remark first before giving an example. In R3, cylinders are given by equations in 2 out of 3 variables, say x and y only, or something like that. And then the cross section is given by the the curve corresponding to the 2 variables. Okay. And then the generator is parallel to the third variable. Here, uh, our generators are our directrix are the x, the y, and the z axis only for simplicity. But of course, it can be any. All right. Here is our example. X squared plus y squared is equal to 25. So what's the graph? This is the graph of cylinder in R3. Of course, in R2, in R2, in R2, it's a circle. So the cross section here is x squared plus y squared equal to 25 in R2. So given by the following, so this is a circle of radius 5 centered at the origin. This is your cross section. So the graph, the sketch of graph is our axis. So the generators along parallel the z-axis. So this is your z-axis, this is our y, and then this is our z, and then situate here our circle, and then here we get our sphere that extends in both directions, of course. But to see a good illustration or picture, just have to cut the sphere into some portion of the sphere. You have cylinder in the normal or in the usual sense. So here, yeah, the generators are parallel to the z-axis. And then the cross-section is just a circle. This is our y-axis and x-axis. Corresponding to what I have mentioned here, cross-section is given the curve in the corresponding to the 2 variables which are present. In this case, x and y. Another example. Okay. So, okay. You can check some other examples in the book. So Z is equal to sine Y in R3 is also a cylinder. So the axis, the cross section is sine graph. So this is our Z, this is our Y, Z, Y, and then the cross section is, let me increase the size. Like it extends in all directions. And then the sketch is, or the sketch of the graph. So you have Z, you have your X, you have your Y, and along Y you get something like this. And then what you will have is our generator will move along this line, along this curve. So something like here, this is the curve. Okay, I'm not drawing properly. It's something like the rooftop or the galvanized iron. So this is our X, your Y, and then your Z axis. This is your Y. This is your Z axis. This is the sketch of the graph of this in R3. Notice we just have two variables, Z and Y, and then the let me have a remark. The generators are parallel to the x-axis, which is the missing variable. I think that's all for today. And then the next topic are quadric surfaces. Then announcement, we have exercise and quiz online to reinforce what I have discussed here. All right. So that's all for this recording.